we love. My name is Marvin Humphrey. I'm one of the co-organizers, along with, there's four of us. Daniel Norman is another one. Lisa Kazmarzik, who is not here this evening, is another. And our speaker tonight, Chris Hiestand, is the fourth. I'd like to take this opportunity to thank our sponsor, Goodtech, who is providing the space and also the food. Daniel's also the CTO of Goodtech. Thanks to Goodtech for all of that. And now the San Diego chapter of Papers We Love, give and take is very important to us, and it's great for us to get to know each other very well, so to sort of maximize that. So I'd like to take this opportunity now to have us go around the room and introduce ourselves and say something brief about yourself. So probably something that what you do for a living, but who knows. So I'll start us off. My name is Marvin Humphrey. I am a back-end engineer, and I used to do a lot of Apache stuff, and right now I'm just doing a little consulting on the side. And Chris, why don't you go next?
Sure, yeah. I'm Chris. I'm a software engineer who's consulting mainly back-end and systems architecture type stuff.
Okay, Daniel, you have pizza in your mouth still? Or let's skip around to the next person over here.
I'm Scott, first time here, and I work on mainly SaaS apps.
Welcome.
Thank you. I'm Sam, and right now I'm doing consulting on like a database engine implementation stuff.
Fabulous. Michael?
Hi guys, I'm Michael. I work for Classy. I'm a data engineer.
My name's Eric. I am a full stack. I work at Qualcomm.
Great.
Mike, I'm a developer. Currently working with an early stage startup to build a mobile app that's cryptocurrency.
Buzzword Central. Awesome.
We also have AI, deep learning, internet of things. So
You're the best. You're making up for the rest of us, man.
But wait, you're not a VCM.
Hi, I'm Stefanos, and I'm a big data architect, currently doing some consulting, cloud and big data technology. And good talk to the wife today.
Hello.
Hi, welcome to Davia.
What's your name?
Theodora.
Theodore. I'm Chris Allman. I'm also new here. So I thought this would be interesting meeting to go to because I worked at a startup before my current gig that was based 100% on using Paxos algorithms to solve some hard problems with file systems. I'm currently a Red Hatter. I've been around engineering R&D and IT environments for a long time.
Well, it's great to have someone here who has practical experience with Paxos. That's really, I'd be interested to hear about that.
Missing from my talk, and so I think some things I'll do.
I'm not the theoretician. I was the solutions architect.
Well, you'll have experience a bit with how challenging it is or not to implement.
The Duke and HDFS. The algorithm was the magic. It was the little black box, but we'll go into that later.
Yeah, we sure will. Gabriel?
Hi, I'm Gabriel. I'm a software engineer independent. It's a healthcare startup in Del Monte.
Awesome. And
I'm Daniel. I'm the CTO of Goodtech here. We write retail software for retail.
great, thanks everybody. And now I'd like to take the opportunity to do something we haven't done in prior months, but we hope to continue doing in every month going forward, and that's actually to talk about jobs and hiring. So if anyone here is looking for work, or if anyone here is looking to hire someone, please take this opportunity to speak up. And once again, I'll start off. So I've been conducting a very low-key search for quite some time. I'm looking to establish something part-time and long-term. And the kind of stuff that I work on, I'm a back-end engineer, and I used to do a ton of stuff for Apache. I worked at I was on the Apache Software Foundation's board of directors for a while and such. So if anybody's interested, give me a holler. And does anybody else want to speak to that? Mike?
So we're looking for Python developers, but keep in mind the early stage startup aspect of it. So if you know anybody who's, junior, intermediate, advanced level Python developer who's looking, let me know.
Awesome. Anybody else?
We're looking for full stack, Ember, Go developers, a lot of different stuff. SREs, if anybody knows, site reliability engineers, or like really engineering heavy DevOps folks. We're looking for all of the above.
I'm looking for clients. So my specialty is kind of Kubernetes system architecture slash contract work on kind of anything that kind of normally fits into that ecosystem, monitoring, alerting, logging, or application development, or helping you guys move to a containerized model. Oh, and Chris just walked in. He's a talented software engineer, but go ahead, introduce yourself, please, because I just did that.
Sorry, my name is Chris. I work for a company called Appfolio. We're in Kearney Mesa. I should do a plug, I guess. We're a SaaS B2B2C legal practice management. We are a Ruby on Rails microservice architecture. We're looking for software engineers from entry level to senior software engineer, principal, all the way up. Doesn't matter. You know, good people that are good. Send it my way. Thank you.
There's an open chair in front of that one.
Yeah, well, I mean,
We'll put this chair right in front of the speaker. How do you like that? That work for you? And there's one other thing on the recruiting front that I'd like to speak of, and that's that the Papers We Love San Diego chapter is looking for presenters. If you have a paper that you would like to present, or if you're interested possibly in presenting a paper, don't know which one, feel free to talk to one of the co-organizers or possibly contact us via the Meetup interface. That's probably the easiest way. Just drop us a line via their little communication app, or just get in touch with us. However, you know, the channel doesn't really matter, but we'd be happy to just talk to you about what you might do, and, or if you've already got a full-fledged presentation, we'd be happy to just give you the thumbs up.
we also have a spreadsheet of ideas.
Indeed.
In a spreadsheet that need presenting.
Yes, yes. So looking at that, classic papers are a great way to start thinking about that, but not the only thing that we do. Like today's paper is not a classic paper; it's a contemporary paper.
I
Or-
object, it is a classic paper.
Okay, well there we go.
It's the classic. And it's the classic.
Okay, for tonight's meeting format is going to be a presentation followed by an informal discussion. Questions are welcome during the presentation. If something's likely to go for a long time, then we ask you to save that for the later for the extended discussion at the end. Also, I should mention that it's very important for this group, to people who run this group and the people who participate in this group, that it be welcoming for all. And to that degree, or in that mode, we have a code of conduct, which I encourage people to look into if they so choose. The other thing is that thanks to Daniel's intense efforts in scrambling here, we have a live stream. We've had live streams for months, and in fact, I really encourage people to take advantage of that. I did last month, and I was able to attend Mike's talk despite not being local at that time. And it was really great that I was able to do that. So thanks very much for making that possible, Daniel. And it's really great that we have that. And also the archived version if you want to go back and see what the talk is. But I should also mention that the talk itself will be archived, and then at the end of the talk, we'll be turning it off, and the extended discussion will not be broadcast and archived. So with all of that business out of the way, I'd like to get to our speaker for this evening. That's going to be Chris Hiestand of Kistek Consulting, who will be speaking on the classic Raft Paper.
Thank you. All right, let me wake up my computer. Very curious, Sam, why it's a classic paper. Classic ideas?
No, it's just going to be considered one second.
Ah, okay.
I believe that credit is better.
Yeah.
Future classic.
Yeah,
It's
yeah.
an instant classic.
Right. Okay, we're on the same page. So I kind of want to start off asking if anyone in the room has implemented Raft. Has anyone knowingly used Raft in any software? Okay. What program?
Rethink DB and Degraph.
Oh, nice. How do you like dgraph?
No comment.
Okay. Daniel, what program were you using that had Raft in it?
I forget it, several.
Okay.
I didn't use it as an end user, so I can't really tell you.
Okay, got it. So my experience is that a couple years ago I built a distributed monitoring and alerting system, and it used etcd under the hood. And I kind of fell in love with the idea back then. So that's why I picked this paper, because, well, that and because I thought this would make a good talk, and because it's a popular paper, so I thought people would enjoy this talk. We'll see. All right, so I'm gonna start off by going over some of the basics, and then we're gonna build from there. So the whole point of this algorithm is to build a state machine, right? And a state machine is just something that stores state, like x equals 1, right? And the state machine is typically on a single node. So how do you make that robust to failure? Well, you expand that to more than one node. But then things become complicated, right? So this is a replicated state machine. This is the figure from the paper. And this isn't necessarily how all replicated state machines look, but this is kind of the Raft model. And so what you can see here is you got multiple servers. They all have their own state machine and their own log and their own way to do consensus. And so with the Raft paper, it kind of assumes or states is that a common implementation in order to make a replicated state machine is you use a replicated log, where you say, in this case, x is 3, y is 1, and then y is 9, and it's all orderly. They're ordered log entries, and then when you replay the whole thing, you end up with your current state machine. So you can't really read the Raft paper without understanding or learning what Paxos is. And because it was synonymous with consensus, it was written in 1989, but there's several problems with it. And people have been using it in various forms. Chubby was mentioned in the paper. That implemented a version of Paxos. There was another one in the paper. Zookeeper used a different model. Anyone remember the third one? Anyways, it was another one, and they basically, Chubby and this other program, they had to kind of use a different version of Paxos because Paxos is not complete in terms of being able to build a replicated system off of it.
Spanner.
Spanner, there you go. Okay, so both at Google, Chubby and Spanner. All right, so here's another little nasty comment about Paxos, right? And so the authors of Raft ended up designing Raft because they wanted to use Paxos in a system, and they didn't understand Paxos, and they spent a lot of time trying to figure out how Paxos worked. They couldn't do it, and these are guys at Stanford. So, I mean, if they can't do it, like, what hope does the average software engineer have of doing it, right? And so they thought there's probably a better way. The senior author, or the later author on the paper, said that he thought that they would reinvent their own consensus protocol, and then they thought they might end up reinventing Paxos. But then at least they would understand it taking that path. But they ended up deciding that they could do something simpler. So this is the state of Paxos, which is, yeah, a little ironic. All right. So when you're designing any algorithm, there's a lot of priorities you could consider. And so these are some of the common ones. And I think cool factor probably isn't acknowledged very often, but I think that's there too. And you might, understandably feel like if you're writing a complicated algorithm and you understand it, like, that's pretty cool. Like, you can do this complex thing. But the downside is, right, anyone else who then has to implement the same algorithm might have trouble with it.
What do you mean by space complexity?
How much memory is used, how much storage is used. So these are what Raft uses. Bolded at the top is it has to be understandable. That was their primary priority. And then they really cared about people being able to implement this on their own. And they knew from experience that no one's going to take Raft off the shelf and just use it as is. You're going to have to modify it a little bit, or there's going to be certain use case variables that you need to tweak, and so they wanted to easily allow people to do that. All right, so one of the ways they make things simple is they minimize the state space, because they, it's pretty intuitive that if you minimize the amount of state, you minimize the amount of interactions with state and the overall complexity of the system. And these are kind of a list of techniques they use to minimize state. All right. Another thing they did that was different than Paxos is they decomposed the problem very differently. They decomposed it into leader election, then log replication, and then safety in these relatively distinct areas. In particular, leader election is very different in Raft. A lot of the guarantees of Raft are built around a strong leader model. And I understand, I don't know Paxos, but I understand that leader election and consensus are actually independent in Paxos. You know any different? Okay.
There's very low emphasis on having a leader.
Okay.
Quorum. It's just having quorum, an odd number n plus n over 2 plus 1.
Right. Yeah. Okay, so let's just get some vocabulary down. We can return to this if we need to. So the log, we already went over what that is. A term is it's equal to the number of elections. It's monotomically increasing. It's sent in every RPC that's sent between servers. So they all have a context to know what each other's talking about. The log index is also monotomically increasing. I didn't see that stated, but I think that's the case. And it's the index for a particular log entry. So then the next two terms, match index and next index, these are specific to the leader's perspective. A follower, when it becomes leader, could have a completely different perspective on what these numbers are. So it's specific to one node. The match index is where it knows that it's the latest log entry where it knows that the follower and the leader are in sync. And because, well, I'll get into that later. And then the next index is the next log entry that the leader will send to the follower. Whether or not it has something written there is independent. Yeah.
So there is one match index per follower?
Correct. Per follower, yeah. Yep. Same with the next index, per follower.
Is the match index the index that the follower has like saved to permanent storage, or is it just what the follower has in memory?
So in memory, yes. I think they leave it to the implementer to decide whether it's stored or not. I'm not entirely sure if it's.
Okay.
I think we could consider it stored for all practical purposes.
Drawing a word out of the Raft Paper, I think the word I'm looking for is committed.
Yeah. So committed is specific to the entire cluster. It's not used for one particular node, I believe.
Okay. Yeah, thank you.
Okay. Yeah.
My interpretation of that was fsync was optional, and that they were not the committed did not entail durable storage on any particular machine, because they talk about copy on write using fork as opposed to techniques using fsync. So I believe that Raft is sufficient for producing a reliable state machine across the entire cluster, regardless of whether or not you actually do fsync on individual nodes.
Right. I think the the copy on write was specific to the snapshot generation. I don't know that did they say that it was specific to writing appending to the log in general. But in any case, I'm guessing that that's right, that it's up to the implementer to decide whether they want to sync it to disk or not. Or whatever.
Certainly, because you need a majority to fail to screw you up. Because you can just lie and pretend you run into this. So
Right,
I'm guessing that
right.
the match index just means the follower has that log entry.
Sorry, say again?
So the match index is just the follower knows that log entry is that one. So it really has the log entry.
Yeah. So let me give an example. So say there's one write to the log. It goes to the leader first. The leader has, let's say in this stupid example, has one follower, right? Its match index is going to be 0 if nothing else has been written. As soon as it sends that log entry to the follower and then gets a positive reply back, it moves that up to 1 because it knows it has 1 and the follower also has 1, and so it knows the follower is up to date. Now, if it gets another write from a client, it will still be at 1 for that follower until it sends the write to the follower and then gets a response back. And we'll see this in action. So if it's still confusing, don't worry, we'll see it. All right. So this is kind of what terms look like. And basically, what a term is a term begins when there's an election. And the one that's really important to look at is term 3, because there's no rights during this term. There's no leader even. This means that they couldn't decide who the leader was going to be, and so they're just going to have another election. So terms don't necessarily mean there was a leader. They don't necessarily mean that there were rights. It means that there was an election. That's all. Yeah.
Is it true that the terms are specific to each node may be on a specific term? That doesn't necessarily mean that each node is progressing to the next term independently of what the rest of the nodes are doing, right?
Yeah, that's correct. Now, the whole consensus part of this is they end up reconciling any differences.
Right. There's some synchronization algorithm eventually.
Yes.
Where people will
converge to the same term. Yeah, exactly. All right. And then this is kind of an aside to everything else. From more of a practitioner point of view, you tend to deploy clusters in these sizes, 3, 5, and 7, odd numbers, because this is the minimum amount of servers you can have or nodes you can have if you want this amount of fault tolerance, right? And then I kind of show the relationship between the majority or quorum and these two numbers. All right. Let's talk about server states. All right. So, yeah.
I didn't read the entire.
Okay. No problem.
Maybe this was answered. Why is there an emphasis on constant random term-oriented way, continuing to re-elect new leaders? Why don't you just find a leader, everything's got done and happy, the algorithm's working great, and then for some reason that leader becomes available, then you
yeah.
Why is it constantly
so it's not. It's not constantly churning.
Okay.
So this next section is going to answer that question more thoroughly. All right. So this picture I'm gonna go into a little more detail than just this picture, but this is the start. Everybody starts up. They have no data about each other than like the IP or host name of where to find the other members of the cluster, and they're all followers. And then when there's then they all time out. One of them generally beats the others to it, becomes a candidate first. And then, well, I'm not going to go into this. We're going to go into this more. So I'm just going to say there's follower, there's candidate, and leader. Every node is going to be in one of these 3 states, like full stop. And yeah, the interesting part is like, how they decide which states to be in. All right. Okay, so something that I thought they kind of, well, that's later in the paper too, but something I thought that was interesting is they kind of bury in the paper that the leader is the only member who can serve reads or writes. The read part I found surprising when I read it. Anywho, let's show an example here. All right, cool. All right, there you go, paused it. Okay, so this is this blank fresh slate that I was talking about, where all 5 nodes here, they just started up, and there's this little gray circle around the brown one, and the gray circle represents the timeout. This is the election timeout. So when the gray, how many people have already played with this Raft scope, out of curiosity? Okay, just a few. Okay, good. Good. So this is going to seem super cool for the rest of you. But like the primary author, the first author of the paper, wrote this in JavaScript, and I stole it and tweaked it slightly in order to make it easy for me to show examples. But anywho, this visualization shows Raft operation for most use cases very well. And then the ones it doesn't show, I'm not going to cover because they're edgy and making something to show you would have been complicated. So anyways, okay. So these are all timing out. Now you can see these circle lengths or circumference lengths are not identical to each other, right? And that's because they're randomly chosen. Because they don't want them all to time out at the same time, because then no one would be able to decide who the leader is very easily. And so what happens is the first one to say, hey, I want to be the leader, gets to be the leader. So the earliest timeout generally wins, not counting network effects and things like that. All right, so here's the first election. Let's wait for S4 to time out, and then blammo. Now it's telling everyone, hey, I want to be leader. And then server 5 gets it first, and server 1 followed by that. And they send replies with there's a little plus in that circle, right? And all of these guys. And that means, okay, we're good to go. We like that plan. And inside here, there's these little circles. And that's how many votes it has to be leader. That means I'm a candidate right now. I'm in candidate state. I have 1 vote because I already voted for myself. And I have 4 possible votes that are just coming in over the wire.
Is there already a leader when this event occurs?
No, there's no leader. Well, there could be in another circumstance, but in this scenario, they all start up fresh. Exactly. Yep, exactly. All right. So now S4 becomes the leader. Now you can see the next index and match index get initialized to 0. This is the log index for each node. And then it immediately sends out heartbeats to every node and says, cool, I got your vote, like I'm still alive, I'm the leader, and this is just confirming we're starting a term. And so, no, actually the previous one, they already started term 2. So it's just confirming, hey, I'm leader, hey, I'm alive, here's a heartbeat. All right, so then it just will go on like this until something stops it. So to answer your question, Chris, let's speed up time here. S4 is still the leader, right? There'd have to be some random or timeout, not random, sorry. There'd have to be some issue in order for this to stop being the leader, right? So the whole point of this, though, is that reliability, so that this replicated state machine still works even when S4 goes down.
On a previous slide, didn't they have some kind of statement about how it's common for leaders to be different ones to be elected? I'm just going to show you that.
It's that any node can be a leader.
Okay.
Not that they often are the leader.
Gotcha. Yeah, there's in the practical sense that anyone who's a leader generally stays there.
Yeah. But we can. Another part of the slide that I thought was important was that All of these nodes have complete trust in the cluster. They all have root access, basically. And that's just built into the algorithm. There's no easy way around that. And so for example, if I say I want this guy to automatically fire the timeout, it's going to start a new election. Let me go back a little bit, or a lot. So it starts a new election.
I'm sorry, I didn't understand that. That one can fire a timeout?
Yep. So this could happen naturally. For example, if this is S3, if node S3 just restarts, then it comes back up. It doesn't know what's going on. If it does, say it hasn't heard from the leader yet. It starts up. It doesn't know what's going on. It says, "Hey, I'm starting a new election," right? And it fires. And so it says, "I'm starting term 3." And so it tells everyone, "Hey, we're in term 3." Right? And they all say, "Cool, I was in 2 before. 3 is a bigger number, so I'm now in term 3." And they all decide to join in term 3, and now S3 is the leader, right? S4 couldn't say, "No, I would like being the leader." Like, no, like it's S3 now. All right. Is that all clear? Any questions?
So if I'm,
So is it possible that, you know, while 3 was rebooting or what have you, that because there was still quorum, right? So you know, enough nodes for the log to progress.
Right.
When it came up, although he has a new term, he's missing log entries. So by actually, so the algorithm is not necessarily optimized to maintain the latest. It's optimized to maintain consensus, even at the expense of backtracking in order to regain consensus.
Correct. Yeah. We're going to see some examples of that later.
I think there's a misconception there in the answer or the question you posed. If a majority of nodes have gotten if 3 went down and the majority of the other nodes got later log entries, and then when 3 comes up and tries to elect itself as leader, it'll fail to become leader because it has to include the actual log index when it asks for an election. And others will say that's too old, or something like that.
So he's going to get negative votes from the other members.
So it's the reason why that would fail is a little bit different. If it was missing a log entry, if 3 died and it had no log entries, and then everybody else wrote log entries, and then 3 comes back up and says, "Hey, I want to be leader," all of the other nodes are going to say, "No, I have a committed log entry that you don't have, and so you're not going to be the leader." Is that roughly what you said?
First come up and say, "Hey, I want to rejoin," before also saying, "I want to be leader"?
No, not necessarily.
The issue that might be confusing things a little bit is that 3 didn't reinitialize. 3 was forced to time out, and what the behavior on timeout is, okay, I'm gonna put up I'm going to become a candidate and ask to be elected.
Right.
Yeah, the candidate RPC includes your latest log entry. So you're saying to everybody, "I want to be a candidate. This is how far I've come," and they can tell right away if it's far enough.
Right. Yes. Cool.
All right.
All right. So a follower is a follower until it has a leader timeout. So it hasn't heard the heartbeat from the leader for the randomized amount of time, and then it becomes a candidate. And it starts a new term when that happens. All right. A candidate is a candidate until it wins an election, right? Becomes a leader of the term it already started. There's another election timeout, or there's an election timeout, and so then it will restart the candidate phase with a fresh timeout, and also with a new term, because the number of terms is synonymous with the number of elections. Or the election was lost. So I haven't gone over the RPC calls yet, but basically it got a term from one of the people it talked to, one of the nodes it talked to, that was greater than or equal to its current term. So append entries, RPC is only sent by the leader. It's not sent by the any followers. And so if someone says, hey, I'm the leader, and even if it's the same term number, it knows it lost the election. Is that clear? All right, so a leader is a leader until a new term is discovered via communicating with the other nodes, the followers. And so that can happen like in the example I showed you where S3 comes back up or it times out too fast or whatever, and it starts an election. And then it wins, and then this leader, former leader, becomes a follower. So this is one reason why they do the randomized election timeouts. And I didn't actually sit down to figure out what equations to use, but this is what the trend should look like of how long it should take, how many elections it should take to pick a leader. All right, so let's look at an example of normal log replication. All right, so in this example here, everybody's already on term 1. Oh, sorry, there's no leader yet. There's no leader yet. Forget that. Speed up time a little bit. Okay. All right, so now we have a leader, S1, and we're in term 2. Let's see. I think I just need to click. All right. So now I'm going to I'm going to pose as a client talking to S1, and I'm going to write. So this write starts out just on S1, and you can see that it's gotten to S3 and S4 already, which is right here. And that's why these guys are sending back the affirmative response. It hasn't quite reached S2 and S5 yet. These boxes have dots around them because it hasn't been committed yet. So let's see. All right. So now and whether it's committed is different from the perspective of the leader and the follower, which I think gets back to what we were talking about earlier. And so S1 is the leader. It has just heard back from the rest of the nodes, and it knows that they all sent back the okay, I just got that log right, and now it knows that it has a met quorum for that right, and it's going to mark that as committed. These other guys, the rest of them, don't know that the leader got their reply okay. It might have been, lost in the smoke signals, and so they don't mark it as committed yet. I think that's correct anyway.
Yeah.
So, okay. So then now on the next heartbeat, the leader sends a empty append entries RPC, but it contains its current term and its current log index of 1. And so when these guys get it, the rest of them get it, they're going to see, okay, the right ended up going back to the leader, and so we're going to also mark it as committed. Now everybody sees this. Okay. And so I can do the same thing, and the leader will keep updating the followers, and you can see the next index and the match index are being updated appropriately.
Am I interpreting that correctly, that it only processes one write per cycle?
Yeah, that's correct. Now, they kind of leave pipelining as an optimization to be done by the implementing party. Yeah.
So so the client that is talking to the leader S1, right? Since the leader first commits before the followers are aware that the log has progressed and there's a new committed state. I'm just trying to understand what is the right behavior from a client perspective. When do you say that I have atomically committed my log?
Yeah. So what the leader does is, as soon as it knows it's committed, it returns a positive response to the client.
But is it possible that all of the followers go kaboom at that point?
It's possible, but if you lose quorum, then you can't do any reads or writes.
I mean, since the leader keeps track of the match index for each one of the followers, right?
Mm-hmm.
It will know when there was a quorum of acknowledgements coming back that these specific followers know that the log has progressed, that this committed state. Why not decide to return back to the client at that point?
I'm sorry, at what point?
So I guess what I'm trying to say is that you mentioned that the leader arrives at the committed state and considers that log to be committed
Mm-hmm.
before he gets acknowledgement, the second phase per se of of communicating to all the followers that, hey, here's the new committed,
So the
index, right?
yeah. So I'm realizing or remembering I should try to repeat questions for people online and for posterity. But the question is about when the leader will reply to the client. When the write was actually committed. And so I'll just try to restate. The leader sends out the write to all of the clients. It doesn't have to hear back from all of them before it marks it committed. The majority system is kind of built into the functionality of Raft. And so all it has to do is hear back from the majority of the nodes, including itself. And once it has the majority, then it knows that it's safe to mark it as committed, and that data is not going to be lost in a subsequent election. And we're going to get into that in the safety section.
Only when it's in the leader state and it hears back confirmations from 2 nodes.
Yep.
Then it's going to unblock the write and say, all right, completed.
Correct. Yes.
I have a question. Do we have an example, or is it possible that the match index and the next index can diverge? So it seems like for any normal case,
Yeah.
the match, or whichever one would be 1 plus.
I think I have seen that, although I can't remember. The question is whether the match index and next index diverge, and I believe they do, but I can't remember the use case off the top of my head.
The next index is on the node and the match index is on the leader. Did I know that was
The leader
No.
keeps track of both of those.
Right.
Definition of the joke?
So the next index is the position in the log that the leader is going to send to that particular follower. The match index is the matching index between the follower and the leader, like the most recent index that they both have.
Wait, actually, I've literally got it in front of me. I'm looking at it. I'm guessing when one goes down and it's no longer getting responses back, it sets the match index that it doesn't know anything because it hasn't heard back.
Right.
When you become it's when you become a new leader and you've never heard from a node before, you don't know what its match index is with you.
Right, exactly. Yeah. So when you've lost communication with the follower, you don't know what the match index is. I just don't remember what the next index
So you're gonna
was.
try to send the most recent one.
Oh, right. You're going to be optimistic
And then
about that.
If it doesn't have it, you're gonna send the next. Sorry, I really didn't realize that I had this in front of me right now.
No, that's good. That's good. That was helpful. Yeah. Sorry, was there a question?
I think it probably has also to do with regulating how much, the throughput on the network, right? So if you have a follower that is way behind, right, you know that the follower is going to need to catch up, right? But instead of sending all that log in one batch, you're gonna increment one index every time that there is a heartbeat or something like that. So you kind of regulate how much you're gonna take the network down in order to get this follower to catch up.
All right. So just to see what we're talking about.
Okay. I'm making an assumption. Yeah.
Right.
Does it include the next index in the heartbeat?
No. It gathers that from the response. So it starts out with a next index, and that's what it's going to send to the follower. And then based on what the response is, it will move the next index up or down, or keep it the same, I guess, if nothing's happened. Yeah. So here we go. We have S2 is disabled, and the leader hasn't been able to talk to it, and so it keeps the match and next index where it is. Let's see, can we get this to, and if it loses state, if we just added a new node instead of the old S2 that we know and love, but we added S6, then the match index would be down to 0. Yeah. And then next index would probably stay at the
I think you can take out
the
one
latest.
node and have the rest of them progress a couple of indexes and then bring it back up. And I think we'll see if it progresses one at a time or cuts it up in one shot.
It has to ask for how many log entries and starting at what position to please replay or please send to me. I can't imagine it's going to send all of them. It may have gone away for a little while, and you don't need to replay all of history, just the past 50 log entries or something like that.
Right. Well, let's move on into abnormal log replication because that's where we're getting anyway. All right. Missing and extraneous log entries. All right. So right off the bat, server 1 is leader. It already has 3 commits, but we don't have quorum. 5, 4, and 3 are down, so they're not going to get those commits. S2 will still take them, but nobody's going to mark them as committed because they don't have quorum.
Clarifying question. S1 is the leader from a previous occasion where the timeout hadn't occurred yet?
So
for these 3 nodes, it had to be elected when the cluster was whole.
Correct.
And then something bad happened, and it's staying leader.
Yes. Yes.
Something else started in the election.
Yeah.
Looks like S2 is trying to start an election now.
I mean, it could be that the other three nodes
think
are
those are-
up and disconnected from the network, and then they're in their own little world.
Well, S2 is hearing from S1, so it's perfectly happy not starting an election.
Exactly. Yeah. So S3's just come back on. S1 just sent it the first log entry, and it's going to, each successive RPC is going to get it caught up to where they're at, and they will have quorum. And so you could see as the first index is being updated into S3, they have quorum, so they're marking it as committed. And then the next time it goes out to S2, S2 should see that it has that this has been committed, and that S2 will then mark that as committed as well. Okay, did both of them.
What happens if there's a request right before that? Does it just queues those?
If there's a request right before what?
Before it's committing entries in the followers, it's going to continue to try to commit what it has already.
So if there's a so I guess I don't understand.
Where like S2 has keep going. Like if you have new requests now.
Okay. Yeah.
It's committed the first one, but now it's got new requests. It's just going to queue those. It's going to continue trying to commit everything in series.
Yes, exactly. When a follower comes online and it doesn't have all the log entries, the basic Raft algorithm is to serially replay the log entries one at a time until it's caught up.
Committedness is tracked by an index, so it's not individual entries being committed separately.
Sorry,
It's
say
like
again?
everything before some index.
Right. Yeah. Everything.
The number it has.
Right. But it specifically sends one log entry at a time. And then they leave pipelining optimization to the implementing party later on. Does that make sense? Or?
It's just that there's an offset in the log, and it's assumed that everything prior to the offset is committed and everything after is not committed, and it advances the offset on the basis of the confirmations that it receives.
Right. Yeah.
I think the point you were making though is that you can learn that multiple entries are committed at the same time, right? Or no?
No, the only point I was making is that being commit, the state that describes what has been committed on the node is just an index.
Yeah.
So there's no, that just sort of clears up any questions about the order in which entries are committed. Because it can only be that the index gets increased.
Right. Correct. Yeah. All right. So let's go back up. Okay. So now the former leader S1 dies. S4 comes back online, and you can see from the state of things that the first 3 log entries are committed, but the most recent 2 are not before S1 died. And S4, so we have 2 extra ones here and 3 missing ones on S4. And so we'll see what happens. Okay, so the old leader died, so we had a new election. Now term 3 has started, and there's quorum. Right. So the first thing that 3 did was it said, I'm going to send you the most recent log. And S4 said, hey, I don't know what you're talking about. I'm way down at 0. That's not going to work for me. Where S3 got a heartbeat, and it said, cool, yeah, we're on the same page. So now S2 is going to just update S4 one at a time as fast as it can. All right. So now we're all on the same state except for these 2 additional logs, and S1 is still down. And reminder, these aren't committed yet. We just got a new request to write in term 3, and that's been replicated across 3 nodes. S1 match with what the quorum decided was the consensus. It had to drop those 2 logs off the end.
We call those proposals, not entries.
Yeah. Is that right? Like, that sounds Paxosy? I don't know.
It is Paxos.
Okay.
But essentially, that's what those were. They were proposals because they hadn't been committed.
Yes, that's equivalent. Yeah.
And it could be that for any node that's offline, it may actually not think it's offline. It may think it's a leader. Meanwhile, another leader's been elected, and those proposals that it's floated the rights that it thinks it's allowed to do, it may turn out once it gets reconnected to part of the cluster again, whoops, none of those get to happen.
Right. Exactly. So the key here is that if it's not committed, you can't count on it being part of the state machine, and that once a quorum that a quorum is basically so there's this strong connection between a quorum being required to create a new leader and also to make consensus about the state machine. And those 2 rely on each other. So that's the way that a new leader isn't going to delete committed state, even if it doesn't have it. Oh, wait, no, sorry. A new leader has to have the latest state, the latest committed state, in order to become leader. And hopefully we'll come back to that if it's still not clear. Yeah.
So then is it safe to say that if we had 3 machines which had the current state, and that's the only condition under which you could actually have a committed proposal, that only one, if you then started an election and all 5 machines decided they wanted to be leader, only those 3 candidates that actually had the most recent ones actually could be legitimate candidates.
Right. Yeah, they had to be committed. They had to have the most recent committed log entry in order to be. Well, they could be in candidate. Anyone could be a candidate state, but to actually get voted in,
Right.
it requires a quorum, right? And everyone in that quorum is going to ask, do you have the latest log entry that I have? And just based on the nature of having a majority, anyone who could possibly be elected to be leader has to have the latest committed log entry. I'm sure there could be a nicer diagram. I think there is in the paper that shows this.
Question, does the paper mention anything about the information of how many nodes are in the cluster at any point in time? Because that seems to be like a crucial piece. And how's that information communicated around?
Yeah, so they don't mention that too much except in one section of the paper, and basically they have a configuration section of the log where they store the cluster state. So
what I'm thinking is the case you were mentioning. It's like, let's say the initial state is that you have 3 nodes, so 2 of them are quorum, and
you'd have to write the new cluster state and have that be ratified by a quorum of the existing cluster for the new configuration to take effect.
Yes, but what I'm thinking is, let's say n nodes, right? So at some point there is a network partition that happens, and half of them are on one partition, half of them are on the other.
So yeah,
if the initial state is small enough, and you know, nodes within one partition. I'm sorry.
They actually in the spec talk about transitioning between configurations. It's very carefully documented.
Okay.
So in fact, you can't wind up.
Okay.
You know, they thought about the problem you're thinking about.
Yeah, because you can have some quorum in an island thinking that, okay, we're still good and we're still progressing, we still have quorum, but the reality is that,
The thing is that you couldn't actually have a quorum in an island because it would actually be the quorum state is part of each of the nodes is aware of that. And in order to get to a state where you'd have that inconsistency, you would need to have the old, as Daniel was saying, have the old configuration ratify that new configuration. And so you can't get from there to here.
yeah, and so. And you kind of have half over here and half over there.
that's not wrong.
Yeah, I mean, especially if you're doing the typical odd number, then you're going to have a majority in one side or the other if you have a partition that kind of cuts through them. Okay, let's see. I don't think anything else happens in this example. Let's see. Oh, something else does happen. S2 dies. Oh, I think that's it. Oh, something else, whatever. I think we got it. How does that look? All right, this is where we were. Oh, this is just S5 catching up when it comes back online. All right. Okay. S5 comes back up. S2 dies. S5 comes back up. Starts an election. All right. S5 doesn't have the log entries it needs to become leader. It didn't even know what term they were on, right? So then they all send back negative, like you don't know what you're talking about, S5, and then S3 times out, starts another election, and now they're on term 5. And because S3 does have the committed logs that the quorum does, it becomes the new leader. Oh yeah, and here you can see they're diverged. So now S5 is being caught up. So it's trying one at a time. Here, load this log. All right. And then it brings them back up. Okay. Let's close you. All right. So let's get into safety. So the leader has complete ownership of the replicated log. Nobody else gets to say, well, I had this update like that I got from a client. Like, can we like install this, please? Like, no, like that doesn't happen. The leader is the one that sends the rights to all of the followers. And the Raft safety has these properties, and these properties are kind of I think a summary of the actual proof of what makes it safe. But I'm not going to get into the proof, but these are good to read. All right, so yeah, leader completeness means there can be no leader with stale logs. So let's take a look at that. Right, so this cluster starts up. S4 immediately dies after joining the cluster and starting term 2. And now there's some commits happening. And actually, now that I think about that, was just part of the previous example at the end there too. All right, so now S4 comes up, it starts an election. It doesn't have any log entry, so everyone's going to say, no, you don't get it. So that's how we keep the leader from from deleting good data that's in the cluster already. And then again, like someone else is going to time out, and then they're going to start a new election. Right? That's why we'll. And then those guys will say, "Yep, we're on the same page. Let's go."
Wait, was what happened in that picture that S4 came up and started a new election, and then
Yep.
As a result of that election failing, the other nodes couldn't continue as was, so another node had to then start a subsequent election.
Correct.
And so, like during that whole time, writes basically couldn't progress.
Correct. Any writes from a client would be blocked, or even reads would be blocked at that time. Cool. All right. Let's see. So this little section in the paper was one of the most confusing for me. It was all it seemed like very clear and intuitive, except for this one section, which talks about committing entries from previous terms. And I could be wrong, but I'm pretty sure that the gist of it is that the leader might have a newer commit that hasn't been committed yet in the cluster, but it also may not have the newest commit that hasn't been committed yet. And so let me show you guys from the paper to give you. Is this in the paper? Yeah.
Sounds like a cleanup. So we've had some type of. Well, you need to create it's a safety issue, right? So leader dies in the midst of process.
Yeah, so the previous leader, right, the previous leader died. There's some unwritten state in the cluster. And so in this case, we can, so it can be this, for example. So here, I think this top thing is a leader. Sorry, top thing, S1. S1 is the leader. Expand that a little. All right, S1 is the leader. And it's catching everyone up and writing state 2. State 2 actually gets written to S3, but before the reply gets back to S1 to mark it as committed, S1 dies, right? And then in this next scenario, if S5 becomes the new leader, it can overwrite these 2s and these 4s with the 3s, and that's totally acceptable operation in Raft. Alternatively, if it didn't die, then it would continue to replicate the 4s. And if S5 joined or rejoined this cluster, this 3 would get overwritten because these would now be committed. Is that clear?
I missed that part. So you can overwrite committed things.
No.
No.
No. This is not committed.
Okay, so with S1,
So
it's not actually committed.
Yeah. Even if and this is, I'm pretty sure about this, but not 100%. Even if S3, no, S3 doesn't think it's committed yet. S3, so S1 in this section right here, S1 wrote 2 to S3. Before it gets the reply, so there has to be another whole round trip before S3 knows it's committed.
The notation's different. I thought, so the boldness just means it's the leader.
Oh,
it's not
sorry.
like the web UI where it means it's committed.
Sorry, yeah, that is very confusing. Yeah, yeah. The comment was the notation is different between the Raft scope UI and this paper. Yeah. All right. Yep. Yep, written by the same guy. It's hard to be consistent all the time, you know? I can relate. All right, let's see. Did we get that? Yeah, we got that. Well enough, anyway. All right, so there's only 2 RPCs required. This is part of the simplicity, right? Request vote, which means I just had an election timeout. I want to be leader. I'm sending out the request vote RPC to y'all, and this contains my current term and my log index, right? And then append entries is sent only by leaders, and it says it says here's my current term, here's my current log index, and it also might have the latest log entry that I'm sending you, Mr. Follower, or Mrs. Follower, or Ms. Follower. I'm not really sure. All right. And then they added one more for snapshot functionality when the leader can help catch up a very far behind follower. Maybe it's been off on a desert island for a few years and it just rejoined civilization. And it doesn't have any of the latest data, but it's part of the cluster. And so the leader will say, here, just like take the whole state machine and install this, and don't worry about these individual log segments. All right. So now we're getting into membership changes, how you change the configuration of the cluster to get back to Stefanos's comments and questions earlier. So in the paper they say this is a novel approach. I guess it is. I hadn't seen it before, but it seems like pretty simple. But I don't know. Raft seems pretty simple too. So anyway, there's 3 phases, right? You start out with the old configuration, the original configuration. Step 2 is a joint configuration where you have the old and the new operating simultaneously. And then after the new is set up and maybe you've like sent some snapshots over to the new node, then the new one is ready and then the old one is deactivated and the new one takes over. And they do this in order to prevent any timing issues or any race conditions by having just a hard cutover between the old and the new, because it's distributed, you can't by definition do that at the same time for all of the nodes. And so you kind of in this kind of safe transactional thing, you set up the new thing, you're still running the old thing, and then when you're totally comfortable this is working, they're both working together, you shut down the old one. All right. So the main point about how this joint configuration in the middle works is it requires majorities, or quorum from both the old and the new configuration at the same time to do anything permanent, to write a log, to make a commit, or to there's something else here. To elect the leader. Thank you. Yeah, to elect the leader. All right. So, do I want to go on this? All right. So, yeah. The paper is also a little bit confusing about this part. It says that any node in the cluster can be the leader at this point, but that's not true. A node, I believe that doesn't, a node has to have this old new configuration log entry in their configuration log in order to become leader. Just like the normal leadership election works. If you don't have the latest configuration log entry, you can't be the leader. So anyways.
But the point is that could be, for example, an old node that's not going to be part of the new configuration, or a new node that's not part of the old configuration.
Yeah, exactly. So this is both for adding or removing nodes. So this is the part of this section that I thought was confusing. Yeah, so when a server believes there's a current leader, it will disregard request vote RPCs, which is not how the visualization works, unless I'm missing something. And so this kind of struck me as odd, and I kind of imagine, I don't understand, like, if something isn't in your configuration, why would you accept a RPC from it? So I think they didn't. Go ahead, Marvin.
I believe the answer had to do with it, how much time has elapsed before it receives that request to vote thing. That will, in fact, if it is less than half of the timeout value, then it believes the leader continues to exist. The minimum timeout value. Basically, enough time has to elapse that it actually believes that a leader has died. Yep.
Okay, maybe I missed that part.
I read it closely because I found the same section confusing.
Okay, cool. So to clarify, the in order for a remove server to cause an election and interfere with the operation of the cluster, of the new cluster, half of the timeout time has to have expired on at least one of the follower nodes. Is that what you're saying?
You know, a lot of times we're getting down in the weeds on this stuff, and I'm not sure that I can answer that exactly. I mean, the point is that they thought about it.
Yeah.
And
my guess was they didn't want to introduce more complication, and so they just stuck with kind of the primitives they already had, and that they would allow the implementer to do whatever they wanted, but I'm not entirely sure either.
Seems like if the confusion is that the web version doesn't support this, it's just because they don't do any configuration changes there, right? So the rule essentially wouldn't apply.
Well, no, yeah, because in the web UI you can time out a node, and all of the other nodes will respond with that, like accepting that as a new leader, all else being okay, regardless
This
of
is
timing.
specifically preventing removed servers removed from the configuration,
Right.
and that doesn't happen at all on the web version.
Correct. Yeah.
Is this about configuration?
Yeah, this is about configuration, not about, like, remove because you're offline isn't what they're referring to.
Yeah, that's not removed.
Yeah, they're saying removed from the cluster. Yeah.
But then why would you receive a request to RPC if something that's removed from the cluster?
Right. So
If you
Because they're saying that it doesn't know that it was removed.
yeah.
So it's just like, it's still pinging out to its friends, like, hey, please elect me.
Okay, but if it's out of the configuration, you would ignore messages from it categorically.
Yeah, that's what I would think.
If you take that percent at face value, it sort of flies in the face of that previous example of visual where it was like, guy timed out, sent a request, and they
well,
immediately.
there's no removal of nodes in the UI.
No,
But it doesn't matter. Like if
implication in that.
yeah.
This person, right? Just as they disregard a request about RPC when they believe the current leader exists, full stop.
Right.
Right, but
Yeah. So I was under the impression first reading that this is about the scenario where a node gets disconnected from the rest of the nodes, and then it times out, and then it struggles around on its own for a while, and then eventually reconnects to the network, and then it sends some kind of request to the RPC, and you just want to ignore that if everybody else thinks that the network's healthy until it join the current node.
That's how I interpret it too, because you could have a cluster with, like 9 or 11 servers, maybe 3 of them are always going down and all this saying, hey, elect me, and you don't want the others to be interrupted in what they're doing because you want the cluster to continue to function as a whole. So it seems like they're constantly having elections because you've got some crappy ones over here.
Right.
To totally impede progress for everybody.
Right. Yeah. So I guess I feel better that other people are confused.
Well, that's just not that's how I interpret that sentence.
But that's not going to solve the problem, right? It's only going to throttle it back because it says half the timeout. So that means that after the half the timeout is elapsed, the request is going to be processed somehow. Right?
So if we have a few exceptionally flaky nodes, it could be a problem, but at least it puts a limit on
Puts a limit on how much destruction we can cause.
Yeah. I'm gonna cap this and we can save that for later. I think that's in my mind, it's still not clear to me, but perhaps Marvin's observation is the right one. Anyway, all right. So now on to snapshots or log compaction. So each member is responsible for its own snapshots. This is twofold. It's to prevent the disk from filling up or from memory from filling up. And snapshots are also used to restore a really out of date follower. All right, so this, and they kind of go into some of the details about, it's the state machine plus it's some metadata so that it can answer the RPCs correctly. There's some timing and some like timing issues that they talk about in the paper, but this is fairly straightforward. It's just snapshots, just simple. What could go wrong? All right. All right, so they kind of put this section of the paper at the end, and they kind of buried the part where they said reads are going to be slow if you use Raft. As soon as I read this, first I was surprised, and then second I thought the people who write or implement Raft algorithm in their own projects, they're probably going to do something to make reads faster.
Key difference between this and Paxos.
Yeah, this is a key difference between Raft and multi-Paxos. What is the key difference?
Well, in the Paxos quorum, the nodes, all of them at any given time in quorum, could be both acceptors, proposers, and readers. And by default, in our solution, everything was always both an acceptor and a proposal. Simultaneously. So it meant that we could tell a nice performance story. In other words, the function that we were basically replacing with a consensus-based algorithm that scaled out between clusters could also scale on the number of nodes in the core. See what I'm saying? Instead of having
you're talking about scaling out reads. You could scale out reads and writes.
Yeah. Okay. At the same time.
Okay, so multi-Paxos has a way to scale reads and writes.
And that's probably one reason why it hurts people's heads and why they decided to do this really cool thing and make a much more understandable way of doing this. But the sacrifice is that you do have this single leader bottleneck. Right.
You do have the single leader bottleneck, but in practice, there's things that you can do to speed it up. Reads in particular are easier to speed up. Writes, not so much, unless you don't care about safety as much.
Easier to speed up in what way?
I'm going to get to that. Chris?
I think I had a later question, but if you suddenly start allowing reads on followers, does it change the read consistency model that you get the expectation from the clients? In other words, do you lose strong consistency and you sacrifice it?
Yeah, but yeah, by default, if you were to accept reads from followers, you would be serving stale data potentially.
Okay, so you would expect to have monotonically consistent reads, or just something weaker than that?
So atomic reads. Sorry, say again. What's the question?
So if you had monotonically consistent reads, you can only view the data as it marched on, the commits as commit index increases.
That seems like an interesting area to explore. Let's hold off on that until the end.
Okay, cool. All right. And then they have a section where they discuss, they kind of prove or at least show evidence for understandability of Raft, and so they do some experiments involving teaching students Paxos and Raft, and then they quiz them on how much they learned and see which side did better, and they took pains to minimize bias, but this is one of these experiments that's it's not perfect, but evidence is something, right? And based on what you hear about Paxos and Raft, this seems like a reasonable conclusion that they ended up coming to, that Raft is easier to understand. Yeah, so they also talk about how this Raft is correct, and they have various proofs. And I'm just going to leave it at that and hand wavy, and there we go. Yeah. All right. So they say performance is similar to Paxos in most cases. Again, optimizations we've talked about. I have heard, and it's consistent with what you said, Chris, as well, right? Your name's Chris, right?
Yeah.
It's consistent with what Chris said, is that Paxos can be faster in some circumstances. But in any case, let's move on. All right, so this is what etcd does as part of its reads. So this gives you an idea what people who are actually implementing Raft are doing. All right, so they allow reads to be served by leaders and followers. So the leader will check with the quorum before they process read-only queries, bypassing the log. I wasn't aware that you even had to check the log, but in any case, it just checks the quorum state machine and then processes the query. Followers will ask the leader to get a safe read index and then process the read-only query. So I'm guessing how that works is the follower checks with the leader and says, "Hey, is this thing? Let's see. I guess it basically it asks the leader to do what it's going to do if you ask the leader to start with. Okay, I guess I'm confused here.
It asks the reader, like I actually had to implement this with the ETCD. It asks the reader for the read index to wait for, at which point, and then what you do is you sit there and wait for that read index if you're talking to the follower, and then you can return your read.
So the follower gets the request, the follower talks to the leader.
Yeah.
Then what does the leader do?
Well, okay, in ETCD, there's two different implementation techniques for this. One uses leases, and the other will just have the leader.
Right, leases are next, so let's skip that.
One will have the leader just send a message to every other, or like use its latest message to every other node to get what the current index is. And then once the leader knows it, it then tells the follower that gave the request. And then the follower knows what index to wait for. And then then you implementing your code know that. And then you implementing your code as the person using etcd/Raft will, once you do get to that read index, you can then serve with a linearizable read.
All right, I didn't quite understand that, so I'm not
it's
going to
a lot
repeat
of
it.
stuff.
But don't worry. Let's just move on for now. We can come back to that if anyone has questions. All right. So then etcd also does lease-based reads, where basically you just assume that this is not going to change for some amount of time, and then you just give that data to the person requesting it. And let's see. Yeah. So this uses the wall clock, Daniel's favorite. So sure.
Actually, do you mind if I interject here?
Sure.
It doesn't actually use the wall clock.
No.
Because with etcd, the actual quote unquote clock is a message you push onto the channel. So it actually relies on your thread getting properly scheduled in a quick amount of time for it to actually work properly using lease space.
Well, I don't know. This is taken from the etcd README about Raft. I don't know. Well, okay. Well, I'm gonna leave that as undecided in my mind. But
this is just
thank you.
One time in my life that I got a chance to be talking about that.
All right. So optional enhancement. Pipelining, flow control, batching. Yeah, other stuff. All right. Consul is the other big project that I know of that uses Raft. By default, it used time-based leases as well. You can also tell it to read in consistent mode, which is the Raft standard, or you can tell it to read in stale mode, which means any follower just reports the latest from its state machine, and so it's very fast, but it's arbitrarily stale. So consul also gives some numbers for their real world performance. It's quite a range, but you can have a big range in terms of hardware, distance between the servers, and networking and so forth. But they say, between, hundreds or thousands of transactions per second. All right, so that's all. Thank you. What's the consensus on Raft?
Thank you, Chris.
Yeah, any questions?
So I'm going to stop the recording now. So thank you, everybody.
Do we have any internet questions?
Not today.
Okay.